After you have unpacked your system, lay out all the components and verify that you have received all the components listed in your bill of sale, including one or more 11008 mainframes, a display, monitor, keyboard and mouse, system cables, the Acquisition Interface Module, or AIM, several preamplifiers, and the power supply mainframe for the AIM. You may also have purchased and received an FPA Evaluation Kit, including a printed circuit board, mechanical lens mount, and lens. The use of an isolation transformer and an AC line filter is highly recommended to reduce the introduction of noise into your system. Before connecting main power, ensure that the front panel power switch is switched to the off position. AC power. Ensure that the main AC power switch is in the off position and that the voltage selector switch is in the correct position for your country's AC power. Connect power and turn on the main AC power switch. Let's begin by connecting the system's signal cables. It is often easier and more convenient to begin cabling the system from the bottom up. On the 41401 clock driver cards, the input connectors are silver and the output connectors are gold. The connectors are numbered from left to right, A, B, C, and D, corresponding to numbered channels 1, 2, 3, and 4. Note the connector ordering on the clock driver connectors. Inputs 1, 2, 3, and 4. The first set of clock driver inputs will typically be connected to the second pattern card output, as the first pattern card output is reserved for the ADC subsystem. When installing the micro D cables, it is important to insert the cable perpendicular to the connector, as the internal pins can easily be damaged if the connector is connected at an angle. The connector should insert with very little force. Tighten this with thumb screws, finger tight. Additional clock driver inputs are typically cabled in order to the third and fourth pattern output. Additional pattern output cables, typically with B and C connectors, will be supplied for any unassigned pattern outputs. These can be used for oscilloscope triggers or any other synchronous timing requirements within your system. To install the sense cabling, start with the long black wire, and insert it into the negative side of the sense for one of the cards. And each cable is labeled to show exactly which card and connector it goes into, and just daisy chain the short cables up to the next card and then the next card. And in this way, all the negative sense terminals are connected in parallel, and the end of the long wire should be connected up to the negative input on the 2-wire sense on the rear of the Keithley DVM. The positive side is connected in a similar fashion to the positive sense terminals, which are the side that's away from the CompactPCI ejector handle. And again, the end of the long wire goes into the positive terminal on the 2-wire sense side of the Keithley DVM. This shows all the sense port on the CompactPCI cards daisy-chained together. If your system includes one or more 4002B mainframes, you will also need a banana to BNC adapter to be connected across the two wire terminals with the tab on the adapter going to the negative side. Use a standard BNC cable to connect this to the sense port on the PI 4002B mainframe. Connect the other end of the sense cable to the sense output on the 4002B mainframe. If you have multiple 4002B mainframes in your system, you may use a BNCT to connect one end to the DVM and the other end to the additional mainframes. Connect the GPIB adapter to the rear of the DVM. If you are using other GPIB equipment with a discrete GPIB cable, you may need to attach the other equipment's GPIB cable before attaching the USB GPIB adapter. Then plug the USB plug cable into any available USB port on the CPU, typically on the rear I/O board. Now we will connect the clock input to the pattern card to any of the 4 available outputs on the clock generator card. All 4 clock outputs are equivalent, and the pattern card may be connected to any of them. The first output connector on the pattern card, J1, is reserved for ADC system timing. The other end of this timing cable is connected to the clock input port on the rear of the AIM. The 20-pair ribbon cable is for the data connection to the acquisition box. This connector also must be inserted directly straight into the connector. The other end of the data cable is inserted into the data output port of the AIM. Ensure that the power switch on the analog power mainframe is switched off before connecting main power. This cable connects the AIM's DC power to the analog power mainframe. And the other end is inserted to any available output port on the 3103D power supply. Before attaching the preamplifiers, verify that the preamplifier power is turned off, as connecting preamplifiers with the power on will damage both. Connect the preamplifiers using both the 25-pin D connector and the SMA signal connector for each channel. Pay attention to the cable labels and the wire list to verify that the correct channels are connected to the correct preamps, as preamplifiers are calibrated in conjunction with the associated ADC modules inside the box. Again, tighten the thumb screws finger tight only. And finally, we can connect our standard PC peripherals, such as a DVI monitor and a USB keyboard and mouse. These may be connected to any available USB port on the CPU board. When the main AC switch has been turned on, the front power switch will begin glowing. The status lights on the CPU board will flash in a pattern for several seconds, and then there will be a system diagnostic beep indicating that the CPU is working properly. The BIOS screen appears, and then Windows will begin booting. Turn on power to the data acquisition system on the 3103. This is the Pulse Instruments production test multiplexer used for automated testing of the clock driver and BIOS cards during system installation and acceptance. The first thing you should do before any installation or verification is go through the bill of materials for the kit and ensure that all the cables, components, and modules on this list are contained in your kit. Including documentation about the proper connection for each of the various tests. And this is the test multiplexer itself. With input connections for the clock drivers, and output connections to either the measurement equipment or to resistive loads, input connections for each of the BIOS channels, and output connections to the measurement devices or to resistive loads. On the rear of the test multiplexer, we have inputs for power, AC power for the entire multiplexer, DC power for the internal switching, and selector pins for the ID modules on each side of the multiplexer. Connect the DC BIOS channels to the test multiplexer using either an SMA to BNC cable for CompactPCI BIOSes or a BNC to BNC cable for PI 4000 series BIOSes. Use the numbered cables 1 through 16, noting that CompactPCI BIOS channels are numbered from left to right and then top to bottom by card slot. So channel 1 is here, BIOS channel 1 here. And on the multiplexer, BIOS channel input 1 is here, 1, 2, 3, 4, 5, 6, 7, 8, etc. through 16. Here's channel 1. Next we connect channel 2. There's a port here that reads to DVM, and this should be connected to banana to BNC adapter. And the negative side, the tab on the adapter should be connected to the negative side of the 2-wire input. If you are not using the test adapter, the test multiplexer, then each BIOS channel could be directly connected to the DVM when prompted to by the test plan. Next, we attach our resistive loads to the various load inputs on the test multiplexer. These are designed to be placed either directly onto the BIOS channels when prompted, if not using the test multiplexer, and when using the test multiplexer, they can be attached using a BNC to SMA adapter. And the correct values will be shown in the test plan itself for 1 milliamp sense, 10 milliamp sense, and 100 milliamp sense ranges. So with all the BIOS channels cabled into the test mux and the output of the test mux connected to the DVM, we're now ready to begin testing. There are 2 sets of inputs on the DVM, front and rear. As shown previously, we connected the sense cabling to the rear of the DVM, and we're connecting the test multiplexer or the bias channels directly to the front of the DVM, and we use this manual switch to switch between front or rear input. Rear input is for sense, both current and voltage. Front input is for voltage output. On the rear of the test multiplexer, connect the AC power input to the AC power source and ensure that the voltage selector is correct for your country's voltage. Next, connect the main DC power output to either the bias side or the driver side. We're going to be testing biases right now, so I will connect this to the bias side. And ensure that the USB cable is connected to the bias side I/O module. Turn on the test multiplexer. This light will go on and you will see lights, LEDs for each of the selected bias and driver channels illuminate as well. We are now ready to begin testing. To run the automated bias diagnostics, go to the C drive diagnostics folder, then open the FAT folder for factory acceptance tests, bias 41702, or the corresponding model number for the biases in your system, and double-click the bias diagnostics pip file. Allow PyDats to launch. And this is the test plan. This is the pip file with the test plans that we want to run. First, we will run setup test, and this is a verification test plan to ensure that all the channels and the sense are correctly hooked up to the test multiplexer and to the DVM. It says switch DVM to sense, so we'll push this to select the rear input, press OK. It'll program each bias channel for a different voltage, and now it'll step through each of the bias voltages in sequence. Press OK to select the first channel, and we'll see that the sense should read minus 7.5 volts, and it will step by half a volt on each successive channel. 7.5, 7, 6.5, 6, 5.5, 5, 4.5, 4. That's all 8 channels through the sense, and now the instructions tell us to switch the DVM to voltage output, which is the front. Select the first channel, press OK to select the first channel, and we'll see the same voltages now through the front of the multiplexer, or through the front of the DVM for voltage output, and again we'll see minus 7.5, 7, 6.5, 6, etc. And this time, we will hear the relays clicking in the test multiplexer as the relays inside the test multiplexer switch. If each step through this test plan increments by half a volt, then we know that the sense circuitry is hooked up correctly and the bias output cables are all hooked up correctly for the actual test. Once the setup has been verified, we will run worksheet setup. We will ask for the operator's name. I'll call this STK. The purpose, factory acceptance, and we are testing the PI 41702 bias cards, and we are going to test 8 channels. This is going to set up the worksheet by opening the template and erasing all the test data and preparing the worksheet to accept new test data. After setting up the worksheet, the next step is to measure the resistive loads that are connected to the test multiplexer. In order for these to be tested automatically using the test multiplexer, we will change some cabling so that the DMM can measure the resistance through the multiplexer. We select the Measure Loads test plan and click Go. If we are using the automatic test multiplexer, we click Yes. And now it'll instruct us connect the DVM cable to the MUX input for channel 1. So this is the cable that is connected to the multiplexer input for bias channel 1, and we're going to instead connect it to the DVM. We may need to use an SMA to BNC adapter, and then switch the DVM to the front input. Now, this cable from the DVM is going through MUX input number 1 through the multiplexer and into the resistive loads. When we click continue, the multiplexer will switch that channel into the resistive loads, take a resistance measurement, and send this data out to our spreadsheet here, here, and here, where these values will be used for calculating sense current. The instructions now remind us to take this cable from mux channel 1, reconnect it to bias channel 1, take this cable from the multiplexer output and return it to the front of the DVM, and then switch the input back to sense. If you are not using the test multiplexer, click No. You'll be instructed to connect load number 1 to the DVM input and set the DVM for front input. Press OK to take the measurement. You'll be instructed to attach load number 2, take the measurement, and finally connect load number 3. It will populate the resistance measurements, and now we are ready to test. Once the worksheet has been set up, we can run our voltage output test. Press go. It will ask which channel we want to start with and how many channels we want to test. In this case, we're going to test all 8 channels for bias output. So we click continue. It asks us to ensure that the DVM is selected for voltage output, which is the front, and we press OK. We'll hear the relays clicking, and we'll see the bias voltage is incrementing 0 through 8, and then from 4 volts up by each bit on the DAC, positive and negative, and then you'll hear the relays clicking when the test multiplexer advances to the next bias channel. I'm going to speed up this video so we run through the rest of the channels much faster, but normally this takes about 30 seconds per channel. To run the bias output test without the automux, choose false for use automux, and you'll be prompted to switch the DVM to the front input and then connect each bias channel in turn. So we'll connect channel 1, press enter, and channel 1 will be tested. And when channel 1's testing is complete, the test plan will prompt you to attach the cable for bias channel 2. Attach bias cable 2, press enter. And you can continue like that for the rest of the test. When the test is finished, the data will be exported to Excel, and there will be one tab on the worksheet for each bias channel that's been tested. Each sheet shows the program voltage, the upper allowable limit, lower allowable limit, and upper allowable limit based on the tolerances, and the actual measured voltage from each channel through the multiplexer and the DVM. And if all the channels have passed, you will see that this channel has passed. Next, we'll select the bias voltage sense. This runs through the same set of programming, but instead of measuring the outputs through the multiplexer and the front of the DVM, it'll measure the sense outputs through the rear of the DVM. So as we tell the system which channels to test, we are instructed to switch the DVM for the rear input. We select OK, and it will run through the same set of measurements through the sense port. Again, I'm going to speed up the video to go through this faster, but each channel will take between 15 and 30 seconds to test. Once the sense testing has been finished, again, the data will be output to Excel, and you can see on each sheet the measurement data compared with the various thresholds. Note that the bias voltage output test must be run before the voltage sense test can be run, because the sense test uses the measured output voltage as the threshold for the sense test. Let's also create an error in our test data to simulate what might have happened if a cable had been removed or misconnected and we have a failure. Let's put a out of spec voltage here, perhaps 3.5 volts, and we'll show that this value is now failing the test. We'll save this data. So now we have a failure. We have a failure in our voltage output test, which also causes a failure in our sense test. Let's suppose we had reconnected that cable and we want to run that test again, but only for channel 1. We'll go back to our bias voltage output test and say, well, I want to start on channel 1 and test only one channel. Press OK, ensure that we have the front selected, press OK, and now it'll test only channel 1, which prevents us from having to test the entire set of channels all over again. The corrected data are now output to Excel, and now our voltage output test passes, as does our voltage sense test. Finally, we will run the bias current sense test. We're going to test all 8 channels, so we'll start at channel 1, test all 8 channels, and we will switch the VVM input to the rear. Our loads are connected to the test multiplexer. The DVM will switch between a voltage reading and a current reading. The measurement from the voltage sense will be divided by the load resistor to calculate what current should have been measured at the sense port, and then that will be compared to the actual current sense. This test takes quite a while, can take up to 60 seconds per channel or more. So I will speed up the video just to get through this quickly, but we are testing every channel in the system, positive and negative voltage, to test positive and negative current. There will be a loop through all selected channels for the 1 milliamp range, the 10 milliamp range, and the 100 milliamp range. At the conclusion of the 10 milliamp loop, the test plan will proceed to the 100 milliamp loop. When the 100 milliamp loop is finished, PyDATS will export the data to Excel, and we'll see the results of our final test. So we can see here that we actually have a failure in the voltage sense, or the current sense, in the 100 milliamp range. And we see it's here because I noticed partway through the test that the load resistor had not been correctly attached. So I'm going to rerun a subset of the test here for channel 1. And we're going to start with channel 1 and test channel 1. To run the current sent test without the multiplexer, select false for use automux, and then select which of the 3 tests you wish to run. You can test some, all, or none of the 1 milliamp, 10 milliamp, and 100 milliamp ranges. Let's demonstrate testing all 3 ranges for 4 channels. You'll be instructed to switch the DVM for the rear input, and then you'll be instructed to attach 6.81K resistors directly to the outputs of the bias channels. Your test and calibration kit will be supplied with at least 4 resistive loads of each value. Note that the 6.81K and the 681K are on 2 sides of the same module.
Attach the 6.81K resistors directly to the outputs. And then click OK to continue. Even with the multiplexer deselected, the test plan does not stop between channels within a sense loop. So you'll see now it has automatically proceeded to testing channel 2. If you have more than 4 channels of bias to test, you may need to move the loads from these channels to these channels in the middle of the test. You can pause the testing at any point by hitting the escape key, and now it is safe to disconnect the load, for example, from channel 1, which has been finished with that test, and attach it to channel 5 without disturbing very sensitive measurements that are taking place. You would not want to do this while the test plan is running, because you don't want to disturb the cables or the loads that are actively affecting the measurements. But once the loads have been attached or moved, you can click Continue and allow the software to continue the test on channel 2. Once the 1 milliamp test loop has completed, you'll be instructed to install 681 ohm loads, and as mentioned previously, these are just on the opposite side of the same module. Turn it around and reinstall these directly on the bias outputs. When the tests are finished and all the channels have passed, choose File, Save As, and save this with a file name with information that typically includes the date of test and perhaps the name of the operator. And that concludes the bias testing. To prepare for the clock driver tests, ensure that the clock driver input and output cables are connected correctly, and the use of an SMA wrench can be very helpful as the connector's spacing is very tight. Once the input cables have been connected, plug in the output cables. Then connect the output end of the cables to the test multiplexer. As with the bias mux, this is channel 1, channel 2, channel 3, etc. Connect the resistive loads to the load inputs for the current sense tests. 2K, 200 ohms, and another 200 ohm load. And then make sure that the output from the multiplexer is connected either to the DVM for voltage and sense testing, or to the oscilloscope for rise and fall time testing. On the rear of the test multiplexer, move the USB cable to the driver mux side and move the DC power cable to the driver mux side. Because these two sides of the test multiplexer have a different ID, PIDATs will need to be stopped and restarted in order for it to recognize the test multiplexer. From the Diagnostics FAT folder, clock driver 41401, load the pip file containing the test plans for the PI 41401 clock driver card. Several devices will show up as unresolved, including a generic GPIB module, which is used only when testing without a PI pattern generator, and the oscilloscope controller if your system does not include an oscilloscope. Click OK. And this looks very much like the DC bias test plan. When we run the setup test plan, it will instruct us to switch the DVM to the rear input, and it will now cycle through each of the 8 channels to check that we have a different voltage on each channel. So plus 2 volts, plus 1.5, plus 1, half, 0, minus a half, minus 1, minus 1.5. After we've checked 8 channels on the high level, we'll go through the low levels. 2.5, 2, 1.5, 1, half, 0, minus a half, minus 1.5, minus 1, minus 1.5. We'll now switch the DVM to the front input and look through the low levels. Minus 2.5, minus 2, minus 1.5, minus 1, minus a half, 0, plus a half, plus 1, plus 1.5. And then we'll cycle through the low levels. Minus 2.5, minus 2, minus 1.5, minus 1, minus a half, 0, plus a half, plus 1. If we had an oscilloscope in our system, we would now switch the multiplexer to the oscilloscope and cycle through the same 8 channels and watch the DC voltages shift. That completes the setup test, indicating that the test multiplexer is cabled up correctly. Once we've verified the setup, we'll want to clear our worksheet, type in the number of channels to be tested, which in this case is 8. Press OK, and it will open Excel and create 8 blank template worksheets with places to hold the test data. Once the worksheet has been initialized, we're going to measure our resistive loads. The instructions tell us to remove the cable connected to multiplexer input 1 and connect it to the front of the DVM. We can use an SMA to BNC adapter for this. Now, the DVM will be switched through the multiplexer and see the same resistive loads that driver channel 1 would see. And we've switched the DVM to the front input. Press OK. The DVM will take 3 successive measurements as the multiplexer switches through the 3 resistive loads, and we'll see we have 200, 2K, 200 ohms, and 200 ohms. It now instructs us to reconnect this cable back to clock driver output number 1. And then reconnect our multiplexer output cable to the DVM. Those values are now entered on the spreadsheet, and we can begin our testing. The first test to run is the driver voltage output test. We can select whether to use the automatic multiplexer, which we are using, and the number of channels to measure, and we're going to test all 8 channels. So we click continue, ensure that the DVM is switched for the front input, and the software and multiplexer will take care of the rest. The DC voltages will cycle through a set of values for each channel, and the results will be output to the Excel spreadsheet. And when the test plan is finished, the results will be exported to Excel, and here we show that all channels passed the voltage output test. Once the voltage output test has been run, we can proceed to the voltage sense test. This looks just like the voltage output test, except that the measurements are made through the sense port on the rear of the DVN, so we need to switch it to the rear as instructed by the test plan. This test will take quite some time to complete, so I will edit the video and return when the test is nearly complete. When this test plan is finished, the voltage sense data will be exported to the spreadsheet, and again we can see that all the channels have passed. The next test to run is driver current sense. And again, when we're using the automatic test multiplexer, all we need to do is ensure that we select the channels and ranges that we want to test, and click continue, and the software and the test notes will take care of the rest. As each channel finishes the test, the data are exported to Excel. As each channel finishes the 10 milliamp sense test, the data will be exported to Excel. When the last current sense range test is finished, the data will be exported to Excel, and this shows that all the major tests have been completed. In most system installations that do not include an oscilloscope, this will conclude testing for the 401 clock drivers. Go to File, Save As, and save this with a file name that indicates either the date or some other test condition. To prepare for the ADC preamp, ADC, and acquisition card tests, apply a 50 ohm termination to each of the inputs on the preamplifiers. Note that the terminations go on this connector, not on this connector. Make sure that the preamplifiers are not touching each other and that they're on a non-conductive surface. If you have placed the preamplifiers on a metal optical table or other bench, just put some sort of insulating material underneath so that they're not picking up conducted noise from other sources. Next, open the test plans as specified in the instructions. Run the clear worksheet test plan. Which will clear out all the data in the worksheet. And then run the test plans as specified. No external equipment is required for these tests. And the software will simply step through a series of DC offset values, sampling frequencies, and filter frequencies, and then export the data to Excel. This first test, which we call the ramp test, is a short test that takes less than 5 minutes to run. It'll run through 91 loops for each of the installed ADC channels, and then export the data to Excel. The Excel worksheet now contains all the data, and there is a bug in Microsoft Excel that prevents these graphs from updating when the data has been newly exported to the sheet. What's required is that you file, save as, save this file with today's date, and then close and reopen it. So we're going to close this file, reopen Excel, select it, and now when we go back to the graphs, they'll display properly. And you should see a relatively flat noise curve for each of the 4 channels. And then for the value graphs, you should see a straight line with a high degree of correlation and a slope that is close to 1. Repeat this for the second ADC and for the double speed test. Next, we will run the more comprehensive ADC test, and that pip file is called Noise versus Gain versus Frequency versus Offset Dual Chip 16-bit 10 MHz. Open this pip file, and the mechanical setup is the same. No external equipment and 50 ohm terminators applied to each of the signal inputs. The first thing we'll do is clear the worksheet, and we'll set the number of outer loops dependent on how many sheets equal to how many outer loops we want to run. I'm going to run an abbreviated test for the purposes of this demo, and then run the ADD noise. And the system will acquire data in a loop, changing the DC offset voltage, frequency, and filter, and at the conclusion of each loop, it will export the data to Excel. This is a much longer test, and depending on the number of loops and the DC increment value you select, it could take a few minutes to many hours. You can see from the status output here which inner loop, medium loop, and outer loop are being run, and at the conclusion of each outer loop, you'll see an export to Excel. And at the end of each outer loop, you will see test results along with pass or fail. This demo system has some failures in it, and the noise levels are a little bit high. But as the test plan proceeds, you'll see all these rows get filled in. And when that's finished, then the test is complete. Repeat this for the second ADC and for the dual chip modes. Once the diagnostics have been completed, remove the test cables from the clock driver and bias outputs and return them to the test mux case, and then attach the working cables for the clock driver and biases that were supplied with the system. Next, we will connect the bias output cables. Channels are numbered from left to right, corresponding to channels 1 through N. And again, it may be easier to connect the channels from the bottom up. The clock driver and bias outputs are now available to be connected to your detector board. Before connecting our focal plane to the system, we are going to run a quick diagnostic test using our clock driver signals to simulate a video device. So we're going to connect our clock driver outputs to the preamplifier inputs. If your clock driver outputs have SMA outputs, you may need to use BNC or SMA adapters. The green terminators I just removed are 50 ohm terminators, and the shorting plug should be used whenever a preamplifier channel is not being used. We can connect clock driver output cables to the preamplifier inputs, channel 1 to channel 1, channel 2 to channel 2, etc. Ensure that the connectors are finger tight. Let's start by loading welcome to pulse.pip. The file name on your system may have a suffix such as 16-bit 10 MHz to reflect the configuration of your system. Once the pip file is loaded, let's open PyPlot. Click on Welcome to Pulse 64 by 256 and click Go. All these steps in the test plan will execute, and the last one will take a data set, and now we have a data set in PyPlot that we can graph. Here we can see that we've misconnected 2 of the channels, and channels 2 and 3 have been swapped. We can switch those back. And now they're set up correctly. And this is what you should see if your system is hooked up properly and running properly. Each of these 64 by 256 sections of the image are being created by one channel of the pattern generator being fed into one channel of the preamplifier. This is a closed loop test designed to test 4 channels of clock driver and 4 channels of data acquisition, and is a useful system diagnostic anytime you have questions about the status of the system. Within the test plan file, we can use our real-time controls by switching this blue triangle from test plan to controller mode, and we can use the define control to turn on only one of the channels. If we can isolate each channel in sequence, or we can activate 2 of the channels, 3 of the channels, or all 4 of the channels. This tells us that the system is working properly. The optional FPA Evaluation Kit consists of an interface printed circuit board with a test adapter installed. These blue wires short the clock inputs to the video outputs. An unpopulated carrier board for the actual FPA, including decoupling and shunts on the reverse side. A mechanical mounting plate with rails for the lens mount, a lens holder, and an optional lens, baffle, and O-ring. Also included are a static strap and a hex key. To assemble the kit, place the FPA side of the board towards the rails and use the included hex head screws to attach the board. Align the board by resting it on the table so both surfaces are flush. Hand tighten the screws and then tighten securely with the hex key. To attach the lens mount, loosen the thumb screws, slide the assembly onto the rail, and lightly tighten the screws so that it slides smoothly. Place the O-ring over the threads on the lens and press fit the baffle onto the lens. Loosen the side screws to remove the top of the lens mount. Place the lens in the holder. Tighten the side screws and then push the lens in this direction as far as it will go and lightly tighten the top screw to secure it in place. The lens assembly is now complete. Once we have verified basic system functionality using the Welcome to Pulse pattern, we can proceed to hooking up our detector evaluation board. First, I'm going to press the green circle to stop the acquisition system, click on the disconnect test plan, switch back to test plan mode, and click go to shut all the clocks and biases off. Next, I can disconnect the clock driver outputs from the preamplifiers and connect them to the FPA evaluation board.
Examine the documentation for your kit to determine which clock signal goes where. In this case, my signals are numbered D1 through D4 for clock driver outputs 1 through 4. The connections for your system may be different. Please consult your documentation. Next, we will connect the bias supplies. For these microbolometers, only 6 bias supplies are required. And again, on my board, the inputs are labeled B1 through B6. Once you've connected your cables, it is a very good idea to double check all the channel numbers to be sure that the correct signals have been connected to the right inputs on the board. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and I will check them at both ends. 1, 2, 3, 4, 5, 6, 1, 2, 3, and 4. Application of the incorrect signal to the microbolometer or any FPA can permanently damage the FPA. Next, we will connect our video output signals. This is video output 1. This microbolometer only has a single video output, but there are 4 outputs provided on this interface board, potentially to support additional FPAs and also to support our test pattern, which I will show you in a moment. We also have a 5th coaxial connector in this bundle. This coaxial cable does not have a center conductor, and we use this simply as a ground connection, as a threaded coax cable provides a better ground connection than the simple alligator clip. This ground connection can be useful in troubleshooting noise sources, although it is often not used. And then connect the signal output cables to the preamplifier inputs. The dummy cable without the center pin can either be connected to an unused input or it can be just left disconnected. With this detector evaluation board, we've also provided what we call the Welcome to Pulse adapter. It is the same carrier board that would normally house the focal plane array, but we've connected the clock driver outputs to the preamplifier inputs to duplicate the setup we just had by connecting the cables directly to the preamplifiers. This allows us to run the same pattern that we did before. Let me turn this back on. This allows us to run the same pattern we did before, but with the detector evaluation board in the loop. After we have verified the functionality of the clock drivers, it is a very good idea also to verify the bias voltages. I still have the Welcome to Pulse adapter in here, and I can either use probe pins to probe inside the socket, which is the preferred method, or for a quicker check, we can just put the voltage probes on the back side of the SMA connectors. So we look at our test plan. Our VDDA should be 5 volts. And I measure 4.99 volts. VDDL should be 3.3. I'm measuring 3.29. VBus should measure 2.8. .79. GFID, this is a tunable bias, which has been set to 3.3 volts. 3.3. I can hold the probe steady. We're at 3.29. VSK is 5.469. I'm measuring 5.47. And the last one is GSK, which should be 2.12. And I have 2.12 volts. So all the biases are functioning properly. All the clocks are functioning properly. And now it's time to plug in our FPA. Again, I attach my static strap. Switch to the disconnect test plan. Shut down all the clocks and biases. You'll see the two LEDs turn off. The FPA is now safe to connect or disconnect. To install the FPA into the FPA Evaluation Kit, first, be sure to wear your static strap. Examine the FPA carrier board. There are 2 rows socket pins and decoupling and terminations on the rear. The 2 connectors are identical, but there is a marking for pin number 1 and a chamfered corner in the outline. With the FPA, here's this similar chamfer on pin 1. This goes here. The pins on the FPA are staggered, and only every other pin gets used. Align both sides and gently press the FPA into place. Remove the Welcome to Pulse adapter, and then take the FPA adapter and put the long row of pins into the top of the socket. Now, reattach the lens assembly and push it tight against the board until the baffle is seated, and lightly tighten the thumb screws. The FPA is now assembled. Installing a flat pack FPA in the socket can be somewhat more difficult because it is very important to keep all the pins aligned as the test socket is closed, and the pins are extremely delicate.